antiderivatives. So if I give you if I tell you f prime of x is equal to 3x squared, what is f of x? What was the original? Sorry? It would be x cubed, right? F of x would be x cubed. Because the derivative of x cubed is 3x squared. All right? However, this is one possible answer. There's actually an infinite number of answers. Why? I can't hear. Yes, it could be any constant. Yes, because if I wrote f of x is equal to x cubed plus 4, does that give me a derivative of 3x squared? It does, because the derivative of any constant is 0. So the actual answer would be f of x is equal to x cubed plus c. Okay? And this is the antiderivative of. Now, c could be 0. That's a number. But it could also be a bunch of other stuff. And we'll learn how to find c in a bit here. So the antiderivative is just figuring out where did this come from? Okay? Where did this derivative come from? So we got a bit of notation here. New notation. We'll talk about what it means later today in terms of why it looks the way it does. The little curvy line is called an integral. This is obviously your function. This is the dx is the variable of integration. And this is basically saying find the antiderivative, okay? Which we represent as a capital F plus C. This is the antiderivative. Of f of x, I should say. So you're going to start to see this little wavy line, which we will call an integral. We'll talk about what that means in terms of actual info it gives you about a function in a bit. But right now, we're just going to practice getting the antiderivatives. So there's some properties, just like derivatives. There are properties or rules, I guess, laws, whatever you want to call them. So we're going to call them integration laws or rules. All right. What is the antiderivative of 0 with respect to x? It's just a constant, right? Because the derivative of any constant is 0. So this would just be a constant. If k is some constant, then just like in derivatives, you can pull it outside of the integration sign. So I can rewrite this as k integral x dx. So constants can be pulled inside and out. You cannot pull a function out. You can't pull like x squared out, okay? But you can pull constants in and out, depending on what you want to do. We'll do 4, the trig ones, and then we'll come back to 3, because that's like the big thing that everybody needs to remember. So if I said, what is the antiderivative of cosine, i.e., the derivative of what gives me cosine? Sine x plus c, right? So if I take the derivative of sine x, I get cosine. What's the antiderivative of sine? Minus cosine plus c. Comma there. Okay, so those are the antiderivative of cosine is sine. The antiderivative of sine is negative cosine. All right. So what is the antiderivative of x to the power of n? Think about how you got this one here. N plus 1? Okay. You were on the right track. What happens to the exponent? We went from an exponent of 2 to an exponent of 3. So you add 1 to it, right? Because that makes sense, because when you're taking the derivative, you minus 1, subtract 1 from it. So if we're doing the opposite, we should add 1 to it. But if you look at this one up here, how did we get rid of the 3? You divide by that new exponent. Okay? So the antiderivative of x to the n is x to the n plus 1 over n plus 1 plus c. All right. Are we ready for practice? This is the one you're going to use the most. Okay, the n plus 1 over n plus 1. X to the n plus 1 over n plus 1. For polynomials. We'll get into other stuff. We have to do other things, but we're going to start out with polynomials, just like we did with derivatives. So, here's our practice. What is the antiderivative of 3x? So it fits this. What's my exponent here? 1. So then I add 1 to it, and I get, remember constants you just ignore, so it's 3x to the 2 divided by that new exponent plus c. No, 3 is a constant. So we essentially are ignoring it and pulling it out, okay? You only add it to the exponent on the variable. How would you check to see if you did it right? Just take the derivative. If you take the derivative of 3x squared plus 2, 3x squared over 2, do I get 3x? Right, because that 2 will fall down. 2 times 3 is 6. 6 divided by 2 is 3. And that has an exponent of 1. And the constant goes away. So you can always check by doing your derivative. All right. What if 1 over x cubed dx? First of all, do we like stuff in the denominator? No, we want to write it with an exponent that is, what am I trying to say? We don't want 1 over x's, right? So we want to rewrite it as x to the negative 3 dx. So what do? Add 1 to the exponent. What's negative 3 plus 1? Negative 2. And then you divide by that new exponent. Tack on a plus c. So you can write it like that. Or you can write it like this. Or you can write it like this. I don't really care. Whoops. Just be aware those are all the same thing. Okay? Root x dx. Oh, you're doing it all in your head. Correct, because you rewrite it like this, right? You don't have to rewrite it. You can do it in your head. That's fine. But you write it as an exponent, and then you add 1 to the exponent. So it's 2 over 2 plus 1 over 2, which is x to the 3 over 2. Divide by the new exponent. And that's ugly, so we're going to clean that up. When you're dividing a fraction, you flip and multiply. And that's your answer. Again, how could you check? Take the derivative, see if you get the original back. Okay, that's how you can do all of these. D. Sorry? Just C? What's the derivative of a constant? Does that have a 0 in it? What number's there? There is a number. 1. Derivative of what is 1? X. So it's just x plus c. So if you have a polynomial like this, now I'm going to show you the long way, and then nobody will ever do it this way ever again. Okay? So if you have a big, long polynomial, all finding the antiderivative with respect to dx, you can break it up into these individuals. So it's the same as this. And then you do each one separately. So 3x to the 6, add 1 to the exponent, divide by that new exponent, so you get 3x to the 7th over 7. And I'm going to write all the c's individually, but you'll see at the end that they all go away. Plus 7x cubed over 3, call it c2, minus 9x squared over 2, call that c3, 4x, whoops, just 4x, plus C4. Does everybody agree with that so far? That makes sense to everybody? Okay. What's C1 plus C2 plus C3 plus C4? What's 4 times C? Just a constant. Okay? So if you add all the individual constants together, you just get a constant. So this is actually just plus 4x plus, and you just go C. That's all I need to do. So what you don't even have to write this step. Okay? You can just go from here to here and just deal with each one individually. 3x to the 6 or x to the 7 over 7. Then do that one, then do that one, then do that one, and then just plug on, write down a plus C at the end, and you're done. You don't have to go through these steps here. Okay? Last one. X plus 1 over root x. So we haven't done one of these yet. But if you have a single denominator, divide it up. Even when we get to the more complex stuff, if you have one of these, divide it off. It makes your life way easier. And again, I'll show you all the steps, but you can do it in one step if you want. It's going to be x over root x plus 1 over root x. Again, we don't like root x's. So it's over x to the 1/2. If you're dividing variables, what do you do with the exponents? Subtract them. So this is 1 minus 1/2, so it becomes x to the 1/2. I'm going to flip that one up. So that's what we're actually doing. Rewrite it this way, because these are way easier to solve than things that have denominators and stuff. We have to learn different techniques for that later on, which we will. But if you can just turn it into some basic variables with exponents, always do that, because we can just use our n plus 1 over n plus 1 rule. So then we can find the antiderivative. So we add 1 to this. So I get 3 over 2, divide by that, so I get 2 over 3. Plus, if you're adding 1 to negative 1/2, what do you get? What's negative 1/2 plus 1? 1/2. So I get x to the power of 1/2 divided by 1/2, which is like 2 over 1. Tack on a plus c and you're done. Plus c is always at the end, okay? So we have been given the derivative, y prime is equal to x3x squared minus 1. They tell us that y passes through the original function y, passes through the point 2 and 4. Okay? I want to know what y is. So y primed is the same as, we learned in derivatives, dy dx. This dy dx equals 3x squared minus 1, and y prime, that's the same thing. Okay? We know we're going to have to find the antiderivative. Right, so this is essentially called a differential equation, a very simple one. So I'm going to multiply the dx to the other side so that I get dy times dx. Now, to get the antiderivative, we have to do the integration. Okay? So you can integrate both sides. If I integrate dy, what do I get? Just y, right? Because we're integrating with respect to y, and the derivative of it has to be 1. So I get y on this side is equal to, what do I get on the other side? What does 3x cubed, or 3x squared become? That becomes x cubed. What does the 1 become? Minus x, and what do we have to tack on every time? Plus c. So that's where we stopped when we were doing it before. However, we have an extra piece of information. They tell us that this equation passes through this point, 2 and 4, which is our x and our y values. So we can solve for c in this case. Okay, so if I plug those in, I go 4 is equal to 2 cubed minus 2 plus c. Six plus c, so c is equal to? So negative 2 is equal to c. Therefore, y is equal to x cubed minus x minus 2. This is called a particular solution. Because we solved for c, we know the exact one that it is. Okay? That's it. That's a very simple differential equation that you can solve. Okay, so if they give you the derivative, you just write it as y prime is equal to this. You know that it's dy dx. Look, you can go basically straight from here to there. Okay? And just integrate both sides. Right? That'll give you the antiderivative. Plug in your x, y values, solve for c, and you're done. Okay, so there's just a couple of questions I want you to do on these ones. Page 251, numbers 35 to, I'll give you 39. 39 odd. 39 is a double derivative, so what do you think you have to do? All right, if I want to know the area under this curve, I can do it. Because it's a curve, it's hard to figure out the area exactly. So we can estimate it by drawing rectangles inside. Okay, 6 rectangles here, there's 6 rectangles here. This one you can see will be an underestimate of the area because I'm missing all of these little bits here. All right, this one, if I draw the rectangles using the left endpoint as my height, I get an overestimate of the area because I'm including all of these. All right. So when you do a question like this, and again, this is usually like 2 classes of going through this and practicing this and stuff. So we're blowing through this really quickly. And I'm not even going into a lot of the details. So here's the overestimate and underestimate. We're doing the graph of negative x squared plus 5, right, which is an upside down parabola, but we're only doing it between 0 and 2. So the parabola normally goes like that, but we're just looking at it between here and here. They want us to use 5 rectangles. You would go through, you would do the underestimate one. See if I can fit this all on one page. I know there's a lot of notation here. This little thing here, this little e, it's called a sigma notation. It means sum. Okay? So we're summing all the rectangles from the first one to the fifth one of the areas of the rectangles. The area is going to be the height of it times its width. That's what this means. Okay? The underestimate, you go through, you have 6.48. The overestimate, you do the same thing, but use a different use the right endpoint. You go through, you get 8.08, which tells you that the area under that curve is somewhere between 6.48 and 8.08. That's a lot of work just to get a broad area, okay? My question to you is, instead of doing it like this, how could we do it so that, like, in terms of overestimate, underestimate, how could we get a more accurate answer?
Find the area of the rectangles and then the triangles.
Okay, that's correct. That would be the actual area, which is what I want to get to, but how could I do it just using rectangles? What would I have to do? How do I get, instead of getting this broad range of an answer, like between 6.48 and 8.08, which is pretty big, 1.5, how could I shrink it down so that I actually get a single answer of what the area under the curve is? What would I have to do to the size of the rectangles? Make them smaller, right? If I make them smaller and do more of them, I'll get a more accurate answer. Does that make sense? How would I get the actual answer? Think of the very first unit that we did. Think of a horizontal asymptote. What's the definition of a horizontal asymptote? Yeah, I know that. But what is the definition? The limit definition. Do an infinite number of rectangles. Okay? So the actual what you would do, and it says triangles. I always say triangles when I mean rectangles. I don't know why. But you do the limit of this. So if you excluding that, this is what we had before. This is the height of the rectangle. This is the width of the rectangle from 1 to n rectangles. If I just say n goes to infinity and you do an infinite number of them, you get the actual area. Okay. If you did that for the graph of x squared, which is, as you will see tomorrow when we do this, you can do in a heartbeat and actually get the answer. This is what the question looks like. There's your answer, 8.83. 8 over 3, sorry. If you do it using definite integrals, which we're going to learn tomorrow how to do it, that's the answer right there. We're not doing this. We're going to do this. Nobody does this unless you're using it in proofs and other things. All right, but this is why we're allowed to do this. Okay, I just wanted to show you where the background. It's not magic that just pops up. Okay. I know. Yeah, it is. Oh, this is a different question. It's x squared. It's not the same function. Sorry. But you get an actual answer because you can see at the bottom here, we get this limit as n goes to infinity because the limit carries all the way through. And we have this 3 over n, 2 over n. As those go to infinity, those go to 0, right? And you're just left with this 2 times this. All right? So those rules that we learned before actually apply. All right. There's another question. Whole bunch of, it's just algebra. It takes a page to do this, and it's just crazy algebra. But it is kind of fun, but we don't have time to do that. So what we're going to do is we're going to go into definite integrals right now. And we're going to learn how to do it the shortcut way. And I won't even say it's a shortcut because it's just the method that people use. It's like if you were going to do a derivative, you don't use the limit definition of the derivative every single time because that would take forever. All right. We used all those derivative rules. These are the integration rules. Okay. So this you need to write down. Okay. So we're going to say the limit as n goes to infinity of the sum of I from 1 to n. I'm just writing this once. You don't have to memorize it. Of f of c delta x equals the area under the graph. That was easy to see. The big breakthrough here is that the area under the curve is equal to the integral of that function. That was the big breakthrough. You can draw the rectangles and everybody kind of see that because it's a visual thing. But what they realize, and it depends on who you talk to, whether you believe Leibniz or Newton, who invented it, calculus, as a side note. You guys ever heard the story of who invented calculus? You probably know. So here's the story of who invented calculus as it was told to me. All right, so area under the graph is equal to the antiderivative or the integral between a and b. What are a and b? A and b are your endpoints of the graph. So if I say, here's your graph, and I want to know the area from A to B, I call this f of x. This integral represents this area. Okay, that's what it means. The right endpoint is at the top, the left endpoint is at the bottom. Okay? Let's do. All right, we'll do the rules, the properties, and then that'll be it for today. All right. Properties. Definite integrals. And when I say the word definite, it means you have endpoints, A and B. What we were doing before, so these are indefinite integrals because they don't have endpoints. Okay, so indefinite has no endpoints. Definite, we have endpoints like this. All right. So if I have an integral from a to a of f of x dx, remember we're talking about area right now. Think about it in terms of area. If I go from one point to the same point, i.e. I'm going nowhere, what's my area? It's going to be 0. If I have some graph like this, and that's A, and I go from there to there, I have no area. There's no width, right? If there's no width, there's no area. So if the endpoints match, the area is 0. If for whatever reason they're flipped one way or the other, and you want to flip them back, or flip them for whatever, you're allowed to switch the endpoints as long as you throw a negative in there. Okay. So I can flip those, but if I do, I have to put a negative there. I have a to b of f of x dx. And my graph, I'll draw it right below. That represents that area. Agreed? If I have some letter C in the middle there, I can break this integral up. 2 if I want that green bit, that would be the integral from a to c of f of x dx. And then if I wanted the red bit, plus the integral from c to b of f of x dx. So you can split up integrals, because it's just representing total area, basically. And I've already talked about these ones, but we'll just might as well they fit in here again. If you have constants, even with definite integrals, I can pull the constant out, k. And what we did before, if I have functions being added or subtracted together, I can break them up. So just give you an example. That's what we did before. If I have 2 to 4 x squared plus 2x, that's the same as area from 2 to 4 of x squared plus the area from 2 to 4 of 2x. And this isn't really a property, but I'm just putting it in here anyway, because it will come up. I'm going to use a specific example here. Negative 2 to 1, 2x. So the graph of 2x is a line through the origin with the slope of 2. Looks like this. Okay, that's y is equal to 2x. If we're integrating from negative 2 to 1, there's negative 2, so it's this area. And then 1 is there, what's this area? Okay. This area will be positive. Okay. If your area or your graph is below the x-axis, all right, we give it, it'll have a negative number. Okay. I know it's weird to think of areas having a negative number, but it just means it's below the x-axis. Okay. And it's always, the area is always back to the x-axis, from the graph back to the x-axis. I think we'll just stop there. It's a natural place to stop. Tomorrow, we're going to do the fundamental theorem of calculus, is how do you evaluate these things so that we don't have to do this stuff. All right. Instead of doing all this, I'll show you how this works. That's what we're going to do tomorrow. Okay. So we'll start with that tomorrow, and then we'll get into more complex integrals where you have to do some substitution stuff. And then we might touch on logs by the end of the week. I know you're all super excited for that. We're going to do derivatives and integration with logs. 10 minutes class left. Hang tight till the bell goes, please. To where I was. I'm just going to turn the video off. 1 sec.